Hi, everyone. So I'm John, and this talk's going to be revolving around cesium being used for SDA and SSA space operations. So kind of a quick agenda here. I'm going to go over a little bit of a background of who LSAS is, what our heritage is, the problem sets that we're trying to help solve, and then the architecture behind our solutions that we're working on for that. And then finally, the last piece is kind of a teaser of some early on R&D stuff that we're working on. So here you'll see who is LSAS. There's a lot of familiar logos here at the bottom. These are all partners of LSAS, but we originated out of the AGI Foundation years ago, and we've been a partner of AGI for 15 plus years. And this has all been revolved around tools like SDK and ODTK that are used for space mission design and for operations of satellites. After that, we've started to develop some of our own solutions that you'll see here on the right. So Terminal and our UMA tools that are all focused around customer-specific workflows and trying to make these tools a little bit more approachable and easy to use, especially once you get to the space operations side of things. So who exactly are the people we're trying to help? And the two things that we're focused on here is both satellite flight operators and then SDA and SSA analysts. So what are these guys doing on a daily basis that really needs 3D visualization is doing things like planning maneuvers, sending actual telemetry commands, monitoring what your satellite's doing, where it's at, what its orientation is, things of that nature. And then once you get to the SDA and SSA side of things, it's collecting sensor data from optical sensors, from radars, from a variety of different things, running OD, which is your orbit determination, figuring out where you are, what your uncertainty is, what orientation that uncertainty is in, and then screening conjunctions as well. So am I getting too close to something? What's my certainty of where they're at compared to my uncertainty of where I'm at? And a lot of these things can be looked at in the raw data form of them, if it's a report or a graph that you're looking at. But a far easier way to see this is actually in 3D. So I like looking at like two different versions here. You'll see the 3D view here is cesium, but this is showing you have a satellite. You can see the spots on the ground that you can talk to. You can see where other satellites are relative to you. You can see if you're in the same plane as a satellite, or you guys are just going to cross, but you're in different planes, you're at different inclinations, things of that nature. Or you could come and start looking at a bunch of graphs, see a variety of dots or a variety of lines, and try to interpret that data to figure out where you are, who you're close to, what your uncertainty is, et cetera. So the spatial context and the 3D context really helps kind of build your confidence in your space operations and your SSA and SDA analysis. So the two tools that we're heavily working with here are tools from ANSYS or ANSYS Government Initiative specifically, but these are going to be used to do your planning and then your space operations. So if you're planning maneuvers, you're going to be using SDK. Off of that, you're going to produce a bunch of ephemeris, telemetry data, or what you hope is your telemetry data. Then you're going to go into ODTK and actually start operating your satellite. You're going to get out things that is your orbit determination, your predicted ephemeris, the ephemeris of the other satellites that you're tracking, and then you can start to look at, hey, what are my conjunction percentages? What are my force models actually looking like? Stuff like that. So on the left-hand side here, you'll see just a couple of different animations showing the 3D viz that really helps produce this data, or helps visualize this data so that you can see what you produced, what the results of that will be. So now we're going to talk a little bit about the architecture around the solutions we've come up with to try and help bring this visualization to the community. So one thing that the LSAS team's been working on is creating some tools that can be utilized to write out this data easily. So we've created a .NET library that we're maintaining right now called Cesium Writer. This is a set of reusable classes and methods that are written in .NET Core to produce CesiumJS code natively. And these can then be used to take anything from SDK or ODTK or anything that's producing propagated ephemeris type vehicles. So this can be aircraft, this can be spacecraft, and create the CesiumJS code for that. It also does static entities right now. So if you're looking at just your like radar sites on the ground, or possibly like a moving vehicle on the ground that's gonna set up and stay stationary for a little while, produce radar data for you or optical data. And then the last thing that it's doing is also doing some basic line of sight computations so that you can start to visualize when I can see something, when I can start collecting data. So on top of that, the Cesium Writer is now being used in 3 different products that LSAS is maintaining and building. And these 3 are our Yuma FD tool, which is built upon ODTK, but it is specific workflows that our customers are using to actually do flight dynamics. So we've built in this Cesium Writer and a Cesium visualization to be able to show this data and give all of the analysts a quick view of what's happening. In ODTK, we've created an embedded visualization tool. So most orbit determination tools, including ODTK, don't really have any visualization. It's all just looking at graphs and looking at a bunch of reports. So we've built a tool that has a built-in visualization. You click a button, you can see where your satellite's at, what your confidence of where it's at is. And then the final one is exporting your mission designs from SDK and being able to visualize those in CesiumJS as well. That's kind of the earliest on of the 3 here. So I'm going to go through the Yuma FD tool and then the ODTK embedded viz tool. So this is Yuma FD. You'll see on the top left there, there's a picture of the overall interface. The far left-hand side is kind of your workflow steps. So most satellite operators work off of more or less a checklist that says like, I need to do this, then this, then this, then this, and I need all of those to succeed in order. And then I'm confident that like I had my OD run well, I know where the satellite's at, and I can produce that ephemeris. So once that all happens, you get a Cesium visualization there of your satellite. You can add in a catalog of other satellites as well. So if you have those, like a rough idea of the TLEs of where all the other satellites are, you can add that in, visualize them all at once. The bottom window here shows a little bit closer in view of this, but it's also showing that we do produce the covariance ellipsoid that's produced by ODTK. You can visualize that in Cesium as well. And then you still get that raw data view as well. So we can extract all that data, still give you all of your plots. You can see your XYZ covariance if you wanted to, or your position uncertainty over time, whatever you're really looking at. And you can do all of this without ever pulling up the desktop tool of ODTK or having to know how to run all of those individual tools. The workflows are just built in. The next thing that we've been working on is the ODTK embedded viewer. So ODTK, the tool in the top left there, typically your center window might just be one plot or one report. We've created an embedded visualization that has an object browser that you would be familiar seeing if you've worked with AGI tools before or ANSYS tools. You can turn on and off entities. You can zoom to entities. You can have multiple in there. And then you get your covariance ellipsoids out. So this will propagate your predicted ephemeris plus whatever you've known prior for that asset. This uses a WebView 2 embedded visualization. So it also has a native web server in it. So if you're trying to pass this to somebody else, you can hand them the files. They can throw them into any web server and just be able to visualize that. And you can pull it up in your native web browser as well if you don't want to actually use the desktop tool. So one of the other things that I didn't mention earlier was how we're using this, how we're using Cesium technology in general to improve our trainings. So a lot of times our trainings have always been, hey, you need to use this desktop tool, and it's going to be somewhat overwhelming jumping into a tool that can do like aircraft propagation, it can do spacecraft propagation, it can do a lot of comms analysis and all this, and you get thrown that all at once. So rather than do that, we've exported data from those tools and then used Cesium stories to quickly introduce like, hey, you don't necessarily understand orbital mechanics. We can use this tool to kind of teach you that, show you it, but it's also dynamic. You can play with it through time. You can scrub back and forth. You can see all of these things. And so we use this to be a lot of our intro courses. You can walk through this, figure out what orbits are, how you would start maneuvering, maybe how you would do something like a Hohmann transfer, and then you can come into the desktop tools knowing a little bit more, knowing some of that, and be able to create those. So the last thing I'm going to go over here is a little bit of a cool new R&D project that we're working on. Anybody who's used Cesium for a long time has known that it is very much a singular central body tool. It is based around either Earth or more recently, as of last year, it's based around the moon as well. But you could only ever have tile sets brought in for one of those entities, and you had some position data of where the moon was, but it was probably just an image, and you couldn't be based around frames and that or anything. So extending this, we are now currently building and prototyping CesiumJS for multiple central bodies. So you'll have a barycentric frame in the center of our galaxy, and then you'll be able to bring in multiple central bodies, have frames based around different central bodies, have tile sets brought in for multiple central bodies as well. So we've gotten to the point where we've got accurate positions of multiple central bodies. We've loaded in tile sets for both the moon and the Earth, and been able to have both of those operating in a singular CesiumJS window.